Hey guys, it's me again. In this video, we're gonna look at some interactivity in Python enabled through the IPython console in JupyterLab. So, in particular, you need to install Node.js and IPy and these are all cross-platform, so you can install them on any operating system that you are. In fact, whatever we are doing in this particular course should be possible in all operating systems. So, once you have installed Node.js and IPy, you can make use of such things. So, let me open whatever we had done in lecture 6 because we will need these things. Okay, so first things first, let me copy this because we're gonna need all of this. So we're gonna import numpy and matplotlib. We're gonna update the plot parameters and export format. Okay, so once this is done, we can declare, suppose, let us do a very simple example. X be np.len space 0 to 2 times pi and y be sine of x. Okay, so let us do a plot of this. Very simple. Okay, so we have a plot like this. So now let me in fact pass a wave number to this. Okay, so wave number we can pass it like this. So 2 pi times k, and then I must define what k is. So let k be equal to 2. Okay, so basically what we are doing is trying to plot sine of 2 pi kx. This is what we're trying to plot. Okay, so because k is 2, we have two waves in the 2 pi domain. If I make it 1, then I have only this. So now, suppose I want to interact with this plot. Suppose I want to change the value of k through a slider. That would be very useful for us to see how the wave changes as k changes. Okay, so in that case, the first thing that we need to do is to convert whatever we have written over here, which is the core of the code, into a function. So let me do that. So def plot sine and let it take only an input k. So because we're taking an input k, we can eliminate this particular line. Let me comment it at this point of time. Okay, so I've commented this line, and because we're defining a function, we need to indent whatever we want inside the function with respect to this. Okay, so everything's indented. Whatever is inside this is therefore inside this function. So let us make a function call. Let me run this. So running this simply loads the function. It doesn't run anything per se. So let me do this. So plot sine 1. So it passes this parameter 1 into the function and makes the plot, because plotting is a part is executed inside the function. The function has no return value, which is fine. It doesn't have to have a return value. Function can simply do something. Okay, so now once we have this, we can do the following. Let us import one more thing. So from IPy import interactive. So interactive is the is the module inside IPy which will help us to make the interactive plots. So now that we have defined this, let me define an object w, and it will be interactive. So now I will pass the name of the function which I want to make interactive. So it will be plot sine. I will just pass the function handle. This is what is passing the function handle, and I will tell that k is the parameter which should be interactive. So after this I will tell that k can take a value from 0.1 to 10, and it should do so in steps of 0.5. After this is done, I must output W. So if I just press W and enter, it will sort of show what W is, or I can also do disp W. Disp is not there, so let me just show what W is. Okay, so it makes this, and we see a bunch of jagged lines because we have not yet increased the resolution of the x-axis. Let me make it 100. That will make things much smoother. So now when I slide around this, I can see how the plot looks like. Okay, this is how I can study this particular plot in a very easy manner. Now suppose I want to pass this resolution also. So let me call this R. I want to pass the resolution of the linspace. Let me create this function. So now we have a function which takes the wavelength or the wave number and the resolution of the line. Now I have to now pass, so I can set some default parameters over here. I can set k equal to 1 and r equal to 2, for example. Not 2 but 20. So defining the function in this fashion, even if you don't pass any parameters, it will call the function with these default values. So these are the default values with which the function will be called. Now what I can do is, so I can run this right away, no problem. It will create for me an automatic slider for R in steps of 1. Okay, it will create for me an automatic slider, and I don't want that linspace should get something which is less than 2. So now, see what happens when I put it to minus 20. Obviously there's an error because a linspace cannot be created with minus 20 number of points. So I must ensure that R is, the slider for R is going to vary from 20 all the way to 200 and in steps of 5. Let me run this. So by default the values are kept at 1 and 20. The slider values are kept at 1 and 20. Now I can change the resolution, so it becomes much smoother. The plot becomes much smoother. As R is reduced, the plot becomes more jagged. Alright, let me increase K. So now the plot looks very jagged. When I increase the resolution, the plot smoothens out. So this is the kind of behavior that we expect. Everything looks fine. Okay, let me in fact open lecture 5 as well. We had done a bunch of fixed point iterations and we had made this plot where different initial conditions, we were trying to see that depending on what initial guess we have, how does the curve converge to the fixed point. So this is the solution, 3.7 something if I remember correctly. So now I'm more interested in, so over here we had swept over a bunch of initial values. But suppose you don't want to do that. You don't want to sweep over a bunch of initial values. You want to select a new guess point and then see how it goes. So let us do this. Let us take this entire snippet. Let us take it to this particular file. Let us try to make that particular plot interactive. So first things first, we need to remove this loop. See, when I run this, it will show a bunch of values because we ran the guess values in a loop. So we don't need to run, we don't need a loop counter for anything. We just need this. So this bit of code should be sufficient. Okay, so x0 is like the guess, perform iterations is the function over here, and that function calls fx, which is over here. So all of this code is self-contained, but obviously I have not, okay, x0 was there from the previous value, so let x0 be equal to 2. Okay, so if x0 starts at 2, it goes over here, no problem. All right, so let us now try to wrap all of this into a single function because we want to interact with this. So let me remove niter and x0. Okay, so we will put all of this inside a function. So def find fixed, and the inputs will be x naught equal to say 2, and n iter will be equal to say 20. So now all of this is inside a function, and the default values, if you don't pass these things, it will be 2 and 20. All right. So with this in mind, let us now just call the function and see what happens. So find fixed, and let's say x naught equal to 3 and n iter equal to 10. So this is what you get. Let me do it for x naught equal to 50, n iter equal to 50. So this is what you get 50 iterations. Okay, so basically this function works, and now we want to interact with it. So we will declare an object w, and it will be interactive. We will pass the function handle, and we will say that x naught can vary from -2 all the way to 5 in steps of 0.05, and n iter can vary from 5 all the way to 50 in steps of 1. That's fine. I mean, this one is redundant. If you don't pass the step, it will count it as 1, but for completeness, let me pass 1. Lastly, we have to display that object. So w is actually like a widget which runs inside your browser, so then you have to display that widget as well. So when I run this is what we have. So when I change the initial value, we get a runtime error because the iterations won't converge if you have any guess value. Okay, so you can see how the shape changes when you change the number of iterations. What happens? Okay, so sometimes if you choose very odd values, it breaks everything, so you need to rerun it. So very few number of iterations, it has not yet converged. Okay, when you change the initial guess, this is how it looks. Okay, it starts at 3 and takes 7 iterations, starting from 0, of course. When you increase the number of iterations, this is what you get. Okay, so this is a very nice way of quickly discerning what is going on in your problem. If you want to analyze a bunch of parameter space, of course you can avoid doing all this. You can make functions, you can loop over all the initial conditions, but this gives you a very raw feel of what is going on. It gives you you can play around with the values. Okay, let us go back to our old file and let us see whether we can wrap something else, something interesting. Okay, so this was the case where the iterations were converging at this point. Let us take this bit of code and let us try to wrap it around another function. So let me run this. Let us see whether it, so we have this plot, no problem. Now let us see how the initial condition converges to that particular solution. Okay, so number of iterations are fixed, x guess. So this is the parameter that we want to vary and see. So for example, I can make it 2. Let me run this. So when you start at 2, this is how it converges, but I want to play around with the initial value. Okay, I want to play around with the initial value, so let us do it. So let us remove this particular line, and we will wrap everything inside a function. So we will call it define, so let's call it cobweb, and the input will be x naught, and let us say the input default is 0.2. So because we're defining a function, whatever goes inside the function has to be indented. It's very important in Python. In Octave and all, you just need to, I mean, first of all, interactive plots are not possible in Octave as far as I know, but commercial software such as Mathematica or Maple, they do allow you to do such kinds of interactive things. And that's the whole charm of it. You can play around with various values. Okay, so we've done this. This is the code. Okay, let us quickly see whether the code runs or not, whether we have broken something. So cobweb, let me call cobweb with 3 as the initial guess. Oh, xg unreferenced. Okay, let's see what we've broken. Okay, so x naught, we, I think it was xg. Let us see. Yeah, it was xg. So we need to remember whatever you pass is sort of the xg that you're using over here. Okay, it is that same variable name that you're using. You cannot define x naught over here and xg over here. So xg is this. So fine, let me now run this, and we do have a plot which shows this convergence. Fine. So now let me pass this to an interactive function. So w equal to interactive, then cobweb xg equal to, let us choose a range from say 0.5 all the way to 5, and say the step is 0.1. Let me run this. We need to display w as well. Just okay. So see how we can see the convergence of the root. Okay, so for guess values on this side, there is obviously something bad that happens. Okay, it flies off to the other side. So that shows you that you need to guess between those 2 points. You cannot guess beyond that point. Okay, excellent. Let me also change the number of iterations. So niter, let me remove it and call it inside the function itself. Let me have by default 5 iterations. This will say go from 2 to 20. Okay, in steps of 1. All right. So if I reduce the number of iterations, you see that you're slowly converging toward the root. Okay, so this is your guess value, and you're slowly converging toward the root. Let me change the guess value. Let me slide the guess value over here, and let me see how this is how the convergence looks like. Okay, so it's quite an interesting way of quickly assessing what is going on. And in our later studies of dynamical systems and all, for understanding how parameter changes can bring about bifurcations, for example, so it will be very useful for us to study that. We can simply change the value of a parameter with the help of a slider, and then understand what is actually going on with the the various other parameters that we'll see. I mean, in the next class we're going to start with dynamical systems, but I thought it is very instructive to cover how to make an interactive widget in Jupyter Lab. And this will be very useful for research scholars who are studying multi-parameter systems. When your advisor comes in and he says, okay, can you change this value and show me, you can simply move a slider and you can show on the fly how everything looks like, provided of course your function runs quite fast. Okay, so with this positive note, I end this particular lecture. I'll see you again next time when we'll start dynamical systems. Bye.